In this module, we will be learning about alkali metal spectra and spin orbit coupling. We have already introduced this partly, but now we will go in more details, and the outline of this module is, we will first discuss the learning outcomes, what we hope to learn from this module. A brief introduction will be given, alkali metal spectra will be discussed in some detail, electron configurations and atomic term symbols will again be introduced, and then Hoons rules and a brief summary. We will learn about multi-electron atoms and their spectra, how we interpret them, and you will also learn about spin and how it affects the spectra of multi-electron atoms, and this theory how it can be extended to atoms which have a single electron in the outermost shell, that is the alkali metal atoms, and you should be able to write down the term symbols for simple one electron systems. Introduction. For atoms with single unpaired electrons such as hydrogen and hydrogen like ions, and even alkali metals which have a single unpaired electron in their outermost shell, it is relatively easy to interpret the low resolution spectra. But when you look at higher resolution, what you find is that their line spectra, they show that each line is a closely pair of lines, and these previous theories like Bohr theory could not explain this. Coming to alkali metal spectra, they have the same electronic configuration as hydrogen atom, that is NS1, and that means that they should display similar spectra. Only the n quantum number is different for the different alkali metal atoms. The inner electrons are all paired and they do not contribute to the total angular momentum. Selection rules, we have already seen. The selection rules are delta n could be anything, delta L can only be plus minus 1 because of conservation of angular momentum, delta M L is equal to 0 or plus minus 1, and the delta ML is equal to plus minus 1, 0. Selection rule, it can only be seen when you apply a magnetic field, when the lines are split into the various ML components, and this is Zeeman effect, and absence of an external field, the different ML values are all of the same energy, that is they are degenerate. The delta L is equal to plus minus 1 selection rules allows transitions from S to P, P to S, D to P and F to D in the emission spectrum. Now these lines were labeled as sharp, principal, diffuse and fundamental according to their nature, and that is how we have this term symbol S, P, D, F for the atomic orbitals. Possible transitions in an atom are usually depicted in a Grotrian diagram, and this is shown for sodium, where we have shown what are the lines which are possible. So we may now understand the splitting of spectral lines in the hydrogen atom. Both the orbital angular momentum represented by L and spin angular momentum represented by S, they are both vector quantities, so you can add them up. That means J is equal to L plus S. So for 1s electron, L is equal to 0, S is equal to half, total angular momentum J is equal to L plus S. We have already discussed this, and this is equal to half, that means it is only due to the spin angular momentum, and the selection rule we have seen is delta n is unrestricted, it can take on any values, delta L can only take on values plus minus 1. So the first allowed transition from 1s is to the 2p orbital, and for this the vector J is equal to the vector L plus the vector S, and this is when you have integers, this is how we add, and L is equal to 1, S is equal to half, you add L plus S, keep on subtracting 1 until you get L minus S. So you have two possible values, 3 by 2 and half. These two states will have two different energies, and now you can explain the hydrogen like spectra why it is split, because the two J values have different energies. Now this different values, J is equal to L plus S, 3 by 2 and half, they have different energies, but for hydrogen atoms the separation between the two J values is very small, and that is why it was not observed initially. But as the n quantum number increases for the alkali metals, it keeps on increasing up till cesium, when it becomes 554.1 centimeter inverse, which is a sizable difference. And since it is also an angular momentum J, the total angular momentum can also have on 2J plus 1 values, depending upon the value of Mj, the orientation of Mj in a magnetic field, and in the absence of a magnetic field they all have the same energy, and delta J selection rule is delta J is equal to 0 plus minus 1, and now we will generalize what we have learned. This we have already learned before, and now we will go on to other atoms. Coming to electronic configurations and atomic term symbols, we will first distinguish between what we mean by electron configuration and term symbol. The electron configurations tell us on which orbitals the electrons of an atom are located. Now, to get the ground state electron configuration, we make use of the three Aufbau principles. Electrons fill orbitals starting with lowest n and moving upwards. No two electrons can fill one orbital with the same spin, and this is the Pauli's exclusion principle, that if two electrons are in the same orbital, they have to have opposite spins. For degenerate orbitals, electrons fill each orbital singly before any orbital gets a second electron, and this is Hoons rule. Now, the electron configuration of hydrogen is 1s1, and that of sodium we have seen is 1s2, 2s2, 2p6, 3s1. For a one electron system, there are three angular momentum quantum numbers: L, which is the orbital angular momentum, and it is also called the azimuthal quantum number; S is the spin quantum number, and J we have seen is the total angular momentum, and it is the quantum number for this total angular momentum. For example, for hydrogen, the total spin is half because it is a single electron. So, S is equal to half, and there are two possible values of Ms, plus half and minus half. The total number of possible spin values, called the multiplicity, is given by 2s plus 1, which is 2 in this case, and this state is termed a doublet. All atoms with single unpaired electron will have doublet states. Now, moving on to two electron systems, the total orbital angular momentum quantum number is denoted by a capital L instead of a lowercase l as for a single electron. You have already seen this. This is the vector sum of the orbital angular momenta of the two electrons, and the possible values are given by, as before, when you do a vector addition for L, to get the capital L, for the two electrons, if the angular momenta quantum number are L1 and L2, you add them, L1 plus L2, take the absolute value of that, keep on subtracting 1 until you reach L1 minus L2. Again we take the modulus of these, we do not take negative values. Similarly, the total spin angular momentum is also given similarly as capital S is equal to mod S1 plus S2, keep on subtracting 1 until you reach S1 minus S2, and the total angular momentum is the vector sum of the total orbital and spin angular momenta. So, its possible quantum numbers are also similarly given as J is equal to L plus S capital up till L minus S capital. Now, we will apply these rules to the 1s1, 2s1 excited state of helium, which you know has two electrons. When it is excited, this is not an allowed transition, but you can excite it to this level somehow, and you get an electron configuration which is 1s1, 2s1. Since both the electrons are in the s orbital, you have L1 is equal to 0 and L2 is equal to 0. So, L can take on only one value, 0 plus 0, which is 0. But S1 is equal to half and S2 is also equal to half, and that is why the capital S values can be half plus half up till half minus half. That means there are only two values, 1 and 0, and when it is 1, 2s plus 1 is equal to 3, and we know that this is called a triplet state. When S is equal to 0, 2s plus 1 is equal to 1, it is called a singlet state. So, we always write, as you remember, it should be written as 2s plus 1 Lj, and the superscript is the multiplicity of the state, and you have two states, singlet and triplet. L is equal to 0, so you have an S state, and J can take on values which are equal to L plus S up till L minus S. Since L is equal to 0, only the S values will contribute to this. So, there are two possible states. One is the triplet state 3s1, and the other is the singlet state 1s0, and this is the excited state of helium, and it gives rise to two states, a singlet state and a triplet state. The ground state has the electron configuration 1s2, so it can only have state 1s0 since both the electrons are paired and they occupy the same orbital and according to the Pauli exclusion principle they must have opposite spins, that is s is equal to 0 because it is in the s orbital and it is a singlet state. So, you have the 1s0 state for the ground state. All closed shell systems, that is when you have all electrons which are paired in filled orbitals, completely filled orbitals, they will have singlet ground states. And this means that all alkaline earth metals, because after hydrogen the next element is helium. Helium has 2 electrons and the alkaline earth metals which follow after this also have 2 electrons in an s orbital, and all noble gases also have filled p orbitals and s orbitals, and that is why all of them have singlet 1s0 ground states. So, whenever you have paired electrons, you do not have any unpaired electrons and all the orbitals are occupied. So, if it is a p orbital, all the 6 electrons are present there, and if it is an s orbital, all the 2 electrons are present there and you do not have any unpaired p electrons, then it is a 1s0, and all these elements will have 1s0 ground states: calcium, helium, magnesium, all of them. The states are termed singlet, triplet, quartet, quintet, etc. according to their s values, and we have already learnt about this. Now, we will take some more examples of second row elements. Lithium is the first one, and like sodium and hydrogen, it has a 2s half ground state because you have a single unpaired electrons, it is a doublet state. This electron is in s orbital, so it is an s state, and half because L is equal to 0, so J is equal to S, and which is equal to half. And beryllium is again a 1s2 2s2, so it has a closed shell singlet because both the 2s electrons are paired, so it is also a singlet ground state and it is 1s0. Now, the next atom is the 5 electron atom boron, and boron, because it has unpaired electrons, because it has an odd number of electrons, it has the electronic configuration 1s2 2s2 2p1. And now you have an unpaired electron, 1s2 and 2s2 will not contribute to the angular momentum because they are both paired electrons and the 1s and 2s orbitals are completely filled. So, we are only concerned with the unpaired electron in the 2p orbital. To write down its term symbol, we will ignore all these, and 2p orbital, the 1 electron we will consider, and this is L is equal to 1 because it is in a p orbital, and S is equal to half because there is a single electron here, and the J values that you can have are 1 plus half and 1 minus half, which is 3 by 2 and half. So, the possible term symbols are 2p 3 by 2 and 2p half. Now, another element which belongs to this row is fluorine. It also has the electronic configuration 1s2 2s2 2p5. Now, you would expect that it is difficult to write down its term symbol because there are 5 electrons which are in the p orbital, but there is a very useful rule that which we call the electron hole formalism. Boron has 1 electron in its p shell and there are 5 holes or vacancies, that is there is room for 5 more electrons in the p shell. And fluorine, it is the opposite. You have the number of electrons is 5, which is the same as the number of holes in boron, and the number of electrons is equal to 5, the number of holes is equal to 1. So, there is an exchange. Compared to boron, it has the same kind of electron configuration, but where there were holes, there are electrons here, and where there were electrons, there are holes here. And in this theory, whether you have 1 electron or 1 hole, the possible term symbols are the same. That is, it also has 2p 3 by 2 and 2p half. Now, before I discuss which one is lower in energy and which one is higher, we will first discuss the carbon atom, which is more complicated because the electronic configuration is 1s2 2s2 2p2, and now you have to deal with 2 electrons. Finding ground state is a simple matter because you can use the Aufbau principle and you can fill up the 6 electrons of carbon like this, 2 in the 1s orbital, 2 in the 2s orbital, and according to Hoons rule, when you start filling up the 2p electron, do not pair the second electron, put it in another vacant orbital, and this is Hoons rule. So, you find that the 3p orbitals and the possible ml values are +1, 0 and -1. So, the total ml value, Again we use capital because we are talking about the total value, and this is given by ml1 plus ml2, and this is equal to 1 plus 0, and so L is equal to 1. ml is equal to 1, and that is why L can have a value equal to 1, and both the electrons have ms is equal to half. So, ms is equal to 1 and s is equal to 1, because both the electrons are pointing upwards, and that is why their ms values are equal to half. So, we can write down the ground state, it is equal to 3p. Possible J values are again L plus S to L minus S, and in this case you have L plus S is equal to 1 plus 1 2, and L minus S is equal to 1 minus 1 is equal to 0. In between you also have 1, because I told you you have to keep on subtracting 1 until you reach L1 L minus S. So, the three values of J are 2 is equal to 1 and 0. So, the three terms are complete terms are 3p2, 3p1 and 3p0. And now we will discuss the question, the important question, how do you rank them according to the energies, so which is the ground state. Now, before I discuss that, I will talk about another fact, that suppose you are looking at the excited state of carbon. If you look at 2p1, 3p1, the possible number of states is 6 into 6, because there are 6 ways that you can arrange a p electron in 6 possible 3 orbitals and 2 spin states, that is 6 possible ways, and similarly the 3p electron also 6. So, the total number of ways that you can fill it up is equal to 36, and L1 is equal to L2 is equal to 1, S1 is equal to S2 is equal to 1. So, the capital L values are 2, 1, 0, and capital S values are S1 plus 2 up to S1 minus 2. There are 2 possible values, 1 and 0. So, the possible states, when L is equal to 2, you have a D state, and the possible values of S can be 1 and 0. So, 2S plus 1 can be 3, or it can be 1. So, you have 3D, 1D. You also have L is equal to 1, for which you have 3p and 1p. You also have S is equal to 1 and 0 for L is equal to 0, and so you have 3s and 1s. So, you get 6 possible states, which are 3D, 1D, 3p, 1p, 3s, 1s. And I said there should be a total of 36 states. Let us see whether we get 36 states. The total number of degeneracy is given by the product of 2s plus 1 into 2l plus 1 for each one of these states. The first one is a 3D state. So, L is equal to 2 and 2l plus 1 is equal to 5, and the spin multiplicity is 3, 3 into 5 is 15. The second one is 1 into 5 and so on. The third one is 3 into 3, because 2l plus 1 for p is equal to 3, and the spin multiplicity is 3. So, 3 into 3 plus 1 into 3, and then 3 into 1 plus 1 into 1, and if you add them all together you get 36 as we had predicted, because 6 into 6 was 36, and so we have got all the states which are possible. But suppose you are now looking at the ground state. The two electrons did find the ground state by putting the electrons according to the offer principle, but then the ground state itself is also a mixture of many states, as we will see. The two electrons have the same value of the principal quantum number. So, that means now we cannot forget Pauli's exclusion rule, that both the electrons cannot have the same spin state. So, there is a restriction that comes, and you find that out of all the terms that we had looked here, detailed calculations show the only ones which are consistent with Pauli's exclusion principle are 1D, 3p and 1s. So, the 3D term, why have we removed that? Now, if it is 3D, you can only get a D state by putting both electrons in ml is equal to 1, only then ml1 plus ml2 will be equal to 2, and but to get S is equal to 1, because multiplicity of 3 means S is equal to 1, S1 plus S2 should be equal to 1, that means both S1 and S2 should be equal to half, and this means that both of them should be in the same spin state, which is not in accordance with the Pauli's exclusion principle, and that is why this is not possible. In this case, the number of possible terms is not 6 into 6, but it is given by the combination 6C2. what you have learnt in probability, it is 6C2, which is 6 into 5 divided by 1 by 2, 1 into 2, and this is equal to 15. And you can check when you multiply these, 1 into 5 plus 3 into 3 plus 1 into 1, if you add them all together, you will get 15 terms. Now we'll go back to the original question, which is the ground state, and this is described by Hoons rule. There are 3 rules. You've learnt about Hoons rules, but that was a simplified form, that before you fill another electron, all the vacant orbitals of the same energy should be filled up. The actual Hoons rules, which take care of all situations, there are 3 such rules. The first one says, of all the possible states arising from a configuration, the one with the maximum spin multiplicity is lowest in energy. Actually, this is the Hoons rule that we know about, that maximum spin multiplicity means that you should not pair 2 electrons until that is the only option left to you. As far as possible, keep them with the same spin in different orbitals, and that means that the highest spin multiplicity out of this is the 3p state. So we come to know that the 3p state is lowest in energy for the ground state of carbon, and this is what we had found earlier also when we had used the Aufbau principle. Now this does not allow us to decide which of the other 2 states is lower in energy, because 1d and 1s have the same spin multiplicity. Now this is told by the second rule, and according to this, that if 2 states have the same spin multiplicity, then you look at the orbital multiplicity. The one with the highest orbital multiplicity is lower in energy, and this means 1d, because d has a degeneracy of 5 and s only has a degeneracy of 1. The 1d state is lower in energy, and so you have finally 3p is less than in energy than 1d, and then the highest energy one is 1s. Now again we come back to the original question. Out of states which have 3p or within the 3p state, within the 1d state, there are states with different j, which one is lower in energy for a particular atom. This is done by the third rule, which says that for states that are less than half filled, the lowest j value is lower in energy, and states which are higher, which are more than half filled, the higher j value will be lower in energy. So for the ground state of carbon, 3p0 is lower in energy because you have 2 electrons in carbon out of a possible 6 electrons which can be accommodated there. So 3p0 is the ground state. So carbon, which has only 2 electrons out of a possible 6, will have the 3p0 ground state. We also talked about the electron hole formalism, according to which oxygen has 2p4 configuration, and that means it has the same number of holes as the number of electrons in carbon, and so it should have the same possible states, that is 3p0, 3p1 and 3p2. Now in this case you have 4 electrons out of a possible 6, so the ground state of oxygen is 3p2 and not 3p0 as it was for carbon. Now we will summarize the different second row elements and what are their term symbols. Starting with beryllium, you find that there are 2 electrons in the 2s orbital, so it is completely filled, it is a closed shell system, and its term is 1s0. Coming to boron, there is 1 electron in the p orbital, and because L is equal to 1, you have p, and because there is a single electron, it is a doublet state, you have 2p half, and because it is less than half filled. Carbon, we have already discussed in some details, it is 3p0. Nitrogen is interesting because there are 3 electrons in a p orbital. You put them in different ml orbitals, and you find that the total L value will be +1, +0, -1, which is equal to 0. So it is an S state. You have 3 unpaired electrons. That means S is equal to 3/2 and 2s + 1 is equal to 4. You first have a quartet state for the first time, and you have the complete term symbol given by 4s 3/2. Oxygen we have already discussed in details, it is the analog of carbon, but here there are the same number of electrons as the number of holes in carbon. So the ground state is not 3p0 like carbon, it is 3p2. So now let us summarize what we have learnt about the energy splitting in due to spin orbit coupling in the carbon atom. In the absence of electron-electron repulsion, all states were degenerate. When you introduce electron-electron repulsion, these were split into 15 microstates. One was 3p, which had 9 microstates, 1d, which had 5, and 1s, which had 1 microstate, and this is shown in the figure. Spin orbit coupling caused a splitting of the J values. Each level had a degeneracy of 2J plus 1, and this final degeneracy remains until you apply an external field. If it is a magnetic field, we call it the Zeeman effect, and if it is an electric field, we call it the Stark effect. So, this is very nicely shown in the figure here, that this is what happens due to different causes, and this is for carbon. Now, this coupling scheme is called the LS or Russell-Saunders coupling scheme, and it applies to only atoms which have fewer than 30 electrons, that is its Z is less than 30, and these are the lighter elements. For heavier elements, there is another coupling scheme which is called the JJ coupling scheme. The total spin is given by the interaction of the individual spins. We add them all up, and that means we add up all SI, I is equal to 1 to n if there are n electrons, and this gives us the total spin angular momentum quantum number, which is given a symbol S. And the same thing is done for the orbital angular momentum, where all the Li values are added up until you get a capital quantum number L. And similarly, for a 2 electron system we have shown here, there is an L1 vector and L2 vector, and these add up to give you the total L values. And once you have the capital L and S values, you add them up to give the J quantum number, and this is also shown in the figure. J is equal to L plus S. Now, I describe the other coupling scheme, which is very different from here. Remember, in the Russell-Saunders coupling scheme, first the individual spins add up, and then the individual orbitals add up, and then you finally add up J is equal to L plus S. So, in the JJ coupling scheme, it is a complete reversal. Here it applies to heavier atoms, and I said that their atomic numbers are greater than 30, and this is called JJ coupling. In this coupling scheme, the spin and orbital angular momenta of each electron first couple. That means you have J1 is equal to L1 plus S1, J2 is equal to L2 plus S2, and instead of first all the L's adding up and all the S's adding up in the Russell-Saunders scheme, here the individual electrons, their orbital and spin angular momenta add together, and then you add up all these J values and you get a capital J is equal to summation of Ji, and the quantum numbers are given by J1 plus J2 up to J1 minus J2 as for all the vector additions that we have performed up till now. So, in this module we have learned a number of things. The first is that there are two kinds of angular momenta. One is the spin angular momentum and the other one is the orbital angular momentum, and they can couple in two ways. Either by the angular momenta of all electrons coupling to give the total angular momentum denoted by a quantum number with the symbol L, or the same way all the spin angular momenta will couple together to give a capital S, and then you write down the term symbol as 2s plus 1 Lj, and for example you can write down 3p, which means that S is equal to 1 and it is a triplet state and multiplicity is 3 and the L value is equal to 1, or the spin and angular momenta also coupled to give the total angular momentum quantum number J. For example, 3p1, J can take on all values from L plus S to L minus S, the absolute values from here. The Hoons rule tells us which of these states is lowest in energy, and this type of coupling scheme that we have talked about is called the Russell-Saunders coupling scheme, and it applies to all atoms with small atomic numbers and normally less than 30. The other kind of coupling scheme is the JJ coupling scheme, and in this all the spin and orbital angular momenta of each electron couple first. That means that here they are strongly coupled, each individual electron will have a spin and orbital angular momentum, and then the final J value that is obtained is by adding up all the small j values, and this is called the JJ coupling scheme, and as I said, it applies to heavier elements.